The mechanism below has been proposed for the reaction of chlorine and chloroform, CHCl3. We can see it's a three-step mechanism here. The first step, Cl2 goes to 2 Cls. Let's look at that. Cl2 goes to 2 Cls. All these are gases, so I'm just going to not write the state. But they give us the K1 for this. The K1, and then this will be K minus 1. Normally we don't have numbers for these until we calculate them later on. But in this case, we're going to put the numbers in here because they'll tell us some information. So K1 is 4.8 times 10 to the third. Is that big? K minus 1 is 3.6 times 10 to the third. Well, you know, big and small depends on what you're comparing it to. And so relatively speaking, are these big or small? Look at the, well, let's look at all the data. And so that's step one. Step two is atomic chlorine plus CHCl3 goes to HCl plus CCl3. Then they gave us K2. You know, K2, this is just one-way reaction here. This is a reversible reaction. So K2 is 1.3 times 10 to the minus 2. And then the final step here is CCl3. CCl3 is what you call a free radical. You know, it has lone pair stuff here. So it's very reactive. Plus Cl, which is another free radical. It's got a lone pair. Yields, not a lone pair, but a lone electron, sorry. CCl4. Carbon tetrachloride. K3 for this is 2.7 times 10 squared. And so the situation is here, we look at this and we say, okay, what is the slowest step of the mechanism? Yeah, times 10 to the negative 2. This is the smallest rate constant, therefore this should be the slowest step. Well, it also depends on the concentrations as well, right? But looking at the rate constant, this one's going to have the highest activation barrier. Sure, since the temperature for these three steps is the same, so this has the highest activation barrier. So the rate of the RDS is equal to K2 times Cl times CHCl3. And so the problem is with this Cl here, right? Cl is a intermediate, so we got to get rid of it. So how do we get rid of it? Yeah, this is going to be fast reversible. We say the forward rate is equal to the reverse rate. Right. And so we get that K1, Cl2 is equal to K minus 1, Cl squared. And then we solve for the Cl. Cl is equal to K1 over K minus 1, Cl2. And then we've got to take the square root of this. Is that right? And then we can substitute that in here. We substitute that in there, and then we're going to get this. We're going to get K2 times K1 over K minus 1 to the 1/2 Cl2 1/2 CHCl3. Something like that. Is that what you got? So the question was, how do you solve for K? You plug in the K values here. This whole thing is your K. Equals K, we call it K prime because it's just a combined K. That's a K. Oh, actually, there's another problem I signed. I was mistaken. This one, there wasn't the weird. There's another mechanism in there that's quite tricky to solve. I must have gotten rid of that problem.
How would you be able to tell which reaction is slow and fast without the Ks?
Without the Ks?
Yeah.
Without the Ks, you're told. You know, the second step is a slow step, or the first step is a slow step. So you would have to have been told, or if you're not told, you guess. And so you only have, you know, if you got a two-step mechanism, you only have two choices. The first step is slow. You try it. Does it work? You can tell if it works or not by if it agrees with the experimental. If that fails, then try the second step as slow. See if that works. If that fails, then you go look for some other mechanism. All right, other questions? Franklin, yeah. Number what? 11. All right, number 11. Methane plus 2O2 yields CO2 plus 2H2O has a rate law of this. So it looks like it's first order in methane and second order in O2. So it looks like the rate determining step depends on a molecule of methane and 2 molecules of O2. And so this looks like it, you know, because looking at this, but you should know something about the combustion of methane. The combustion of methane is what? Does it occur in one step or many, many steps? Many, many steps. You know, it was said that over 2,000 steps have been figured out for the combustion of methane. That's a lot. So, with that knowledge that the combustion of methane is quite a complicated mechanism, do you think this is likely to be true or likely to be false? You know, something like this says either it's got a weird two-step mechanism like one earlier, like NO2, or it's a termomolecular, it's a single 3-molecule collision. A single 3-molecule collision, is that likely or unlikely to happen? It's highly unlikely to happen. And so the best answer for this one is that it's false. It's unlikely. It might be true, but the chance of it being true are much smaller than the chances of this being false. False is a better answer. All right. What else? All right. me talk about this from chapter 19, delta G and equilibrium. Which is K. When delta G is equal to 0, or delta G naught is equal to 0, then is there any driving force for spontaneous reaction one way or the other? No. This we say is at equilibrium. So both reactions are occurring at the same rate. This is equilibrium. So, what we can see is something interesting that's going to happen. So, for example, this. Let's just say we're under non-standard conditions. We'll just say that, let's look at delta G first. So if we have delta G is equal to 0, this is at equilibrium, and this is equal to delta G naught plus RT ln of Q. Okay. Well, if we're at equilibrium, if we're at equilibrium, sorry. If we're at equilibrium, then Q, has the right concentration and the right pressures to equal K. So Q is equal to K at equilibrium. And therefore, we could rewrite this equation. Delta G is equal to 0, which is equal to delta G naught plus RT ln of K. And that means that delta G naught is equal to minus RT ln of K. And so a big equilibrium constant means products are favored or reactants are favored. If K is big, then delta G naught is highly negative. Right? If K is very small, like say much smaller than 1, then delta G naught becomes highly positive. And so there's a relationship between K and delta G naught. And so let's take a look at that relationship. In fact, let's calculate some Ks. We know how to calculate delta G naught, but in this chapter we'll learn how to calculate Ks as well from Appendix D. And so let's say determining Ks from Appendix D data. To determine K, all we do is solve this equation for K. And so divide both sides by negative RT, and then get rid of the ln. And so we get K is equal to E to minus delta G naught over RT. Yeah. See, we have this. That's one form. And so we could calculate K's based on this. We determine delta G naught from appendix D for any reaction, and then we can determine K for any reaction. And so let's take a look at some of these. So what we'll do is we'll just plot out some delta G naught values and then look at the K values associated with that. And so what are some typical delta G naught values? Well, what we're going to do is we're going to look at minus 200, actually, no, plus 200, plus 100, plus 50, 0, minus 50, minus 100, minus 200. This is going to be in kilojoules per mole. And so can you calculate the K values for that? And complete that table for me? This is a table. I was going to show you this table. I'll save some time, but I might as well just calculate it.